Hey everyone, I'm Bodie Franklin. Today I'm here to talk to you about the math of reinforcement learning. We're going to go over how this algorithm works from a mathematical perspective. So when you're using this algorithm in practice, you'll have an understanding of what's going on behind the scenes. For starters, what is reinforcement learning? You hear about it all the time, but let's break it down. So it's essentially an algorithm that attempts to solve reward-based problems. It learns by doing. It has a feedback system. Some applications of it are self-driving cars. That's probably where you hear about it the most. People are using it to trade stocks. You can use this to play video games. Really, people are interested in reinforcement learning because you don't need to set up a control system. It's setting itself up. So let's talk about the workflow. So the algorithm or agent will interact with the environment, which is going to be the problem. And based on the feedback it gets, the agent will modify its actions. So, for instance, let's say this environment is a robot. The algorithm is going to try to teach the robot to walk. And then, based on it falling or continue to walk, that's going to be its reward function. So, the observations are the angles of joints, the velocity, and the pixels the robot sees. The reward function will be much higher if the robot continues to walk, but if it falls, it's going to have a lower reward function. Again, since this is driven by a reward function, the agent is going to be greedy based. It's going to keep trying to get the robot to walk because it wants that higher reward function. So, a huge part of reinforcement learning is the optimal policy. The agent will use reinforcement learning to discover the best policy that will maximize the reward. So it wants to find the most efficient way to get the highest reward score. And again, the reward is the reward function. That's the goal of the algorithm. It wants to get the highest reward function. It represents the goodness of the agent being in a particular state and taking that particular action. Rewards can be calculated from a nonlinear function or calculated using thousands of parameters. It really just depends on how you want to train your agent and what's the most effective way to train your agent. The decision process is a huge driving factor behind the reinforcement learning. It's a sequence of states if and only if the probability of moving to the next state depends on the present state and not the previous. It means now influences the future, not the past. We only care about what's going on right now. We don't care about what happened 2 seconds ago. The following equation allows us to think about chain as time homogeneous, meaning the probability of transition is independent of t, which is time. We'll define the Markov process as a tulip of SP. S is going to be a set of states. It's finite. P is the state transition probability matrix. So we will start in some state SO and move to succession state S1, drawn from PS1, S2, which represents the probability state 1, state 2. And then again, think of it as a tulip. S is a finite set of states. A is a finite set of actions. We'll be in one state. We'll take one action, like we'll go left or go right. That's considered an action. P again is the state transition probability matrix. Gamba here is called the discounting factor. We'll go in that later on, but we're going to end up discounting some of our action and state values. And then the reward is state times action, and this is just a reward function. So going forward, and the equations in this video R defines the reward function. So the return. So again, reinforcement wants to maximize the value of return. So we need to find the optimal policy. Return is GT discounted from time step T, Gamba. But why are we discounting? Discounting factors allow us to avoid cynical Markov processes due to the property of geometric series. There's an uncertainty about future reward. So if the reward is financial, immediate rewards may earn more interest than delayed rewards. And then again, animals and humans behavior shows a preference for immediate reward. We're not designed to think long term. So again, in order to get the maximum reward, we need the optimal policy. We'll define the optimal policy with this equation here. But in order to get the optimal policy, we have to find the state valued function and the action valued function. Remember, policy is a distribution over actions in a given state. It's time independent. So what is the state valued function? Well, it's a function that gives us the long-term value of state when we follow the policy. We can break this equation down here further into two parts. We can break it down into the immediate reward, the reward we get from performing the action right away, and then we can discount the value of our succession states. So the combination of these two, or the sum of these two, would be our long-term value we get. So an example of this would be you eat pizza, it's amazing, you're loving life, it's the best pizza you ever had, but the next day you feel sick because you're allergic to dairy. Shocker. So your long-term value you're getting from this would not be very high. So your discounted value would be pretty low, but your immediate reward would be pretty high since you are in heaven eating this pizza. I'll go into the discounting value section of this in a second, but for now, that's the main premise of the state value function. So jumping into the action value function, we'll define it with this equation here, but we're able to break this equation down more by defining the action value function in terms of the state value function. And we need to be able to do this in order to get a Bellman equation. And the point of the Bellman equation is it helps us solve the Markov states with X amount of states. And depending on the amount of states we get, we'll get X number of linear equations. And then again, we'll solve for these linear equations in order to get the optimal policy. So we're breaking this down to do linear algebra and solve for linear equations, which we see down here through this workflow. So how do we find the optimal value function and policy? Well, we just defined action valued and state value, and we showed how to solve for that. But we have to get the optimal state value through this equation here and the optimal action value here. But in order to solve for these two through linear equations, we have to define some policies. We have to define the partial order of policies in order to solve for these. So the optimal policy is better than equal to all other policies. The optimal policy achieves optimal value function. The optimal policy also achieves maximum value function by maximizing the action value over all the other actions. But in order to get this again, we have to use the Bellman equation. So if we express the action value function in terms of the state value function, we'll get the following equation down here, right? So again, defining action value in terms of the state value equation, this allows us to solve for the optimal value function. So now after solving for that, we want to evaluate the policy. We can evaluate the policy by solving for linear equations. We assume the Bellman equation is true. So if we start at V1, we'll get an updated valued function of present iteration at the same time based on the previous iteration. At each iteration, k plus 1, for all states, we update vk1 from vks0 according to the Bellman equation. We'll stop until the maximum difference between the value function at the current step and previous step is smaller than some positive constant we define. So again, we're going to iterate through this, and then this is what the iteration looks like from a mathematical perspective. We determine policy after step, policy PI. The iteration will improve the value from each state over one step per equation 1. The iteration improves that value through the following equation, and then we'll stop once the Bellman equation has been satisfied. So once this equation here is satisfied, that's when this iteration stops. So another option to find the optimal policy and value function is value iteration. So for each state, the initial state will be set to 0. We'll use this equation here to find until the max difference between the valued function at the current step and the previous step is smaller than the small positive constant we define. And then we're going to update this function continuously through this iteration. And we'll use this equation in order to get the optimal policy from the optimal function. So now, once we perform our value iteration, we can use this equation here, which is the convergence equation. So what this equation is telling us is it measures the distance between two state values, u and v, by the largest difference between the state values. We can rewrite this equation using the Bellman equation into a matrix form. So this equation here translates to this in matrix form. Then using this backup operator notation here, we're in this theorem here, for any metric space V that is complete under an operator TV, where TV is a gamma constriction, T converges to a unique fixed point at a linear convergence rate of gamma. So essentially what this is telling us is we can just use linear algebra to solve for a system of equations. And that is how reinforcement learning is. We're using linear algebra at the end of the day to solve the state valued function and the action valued function. And that's the end of my presentation. I hope you took a lot away from it. I hope you now have a better understanding of the math behind reinforcement learning. And feel free to let me know what you guys think in the comments below. And here's the works cited I followed for the presentation. Great. Thank you so much.